Okay, this one is especially challenging. And if we are dealing with the integral test, then we have to have a series where the function that I am using for the integral is positive, continuous, and decreasing, and it is. And so I'm going to be looking at the integral from 1 to infinity of 1 over x squared dx. Now, if I look at the possibilities, and I filled in those boxes with d's because that's what they were supposed to be, I need to take a look at what I'm working with. I am working with, there's one of my sigmas, that's the same exact sigma, and this is still the same exact sigma, so is this. So all of them are dealing with specifically sigma from 1 to infinity of 1 over n squared. Now, if I take a look at my integrals, I will notice that I have a starting at 1 and a starting at 2. On top of that, I have a little plus 1 floating around on some of them. So let me emphasize the plus 1s where they show up. And then I want to pay attention to also whether the integral is beginning with a 1 or a 2. And I found a d I did not put in. There we go. So I'm going to draw a picture. And I'm going to have this be approximately 1. And I'm drawing the graph of 1 over x squared. And I'm just going to go with saying that this is about y equals 1 just to get this going. Now, if I decide to compare this with sigma that starts at n equals 1 with the same formula. Hold on, I must let my dog out. Yeah, the dog was wanting a cookie and finally realized that wasn't happening. Back to this. Let me go back to, I'm dealing with the integral from 1 to infinity of 1 over x squared dx. That means starting at x equals 1, this is equal to the area under the curve, all of this, all the way down to infinity. If I want to work with who's greater or larger when it comes to the integral and the series, I want to make sure that the first term of the series is looking at what's going on between 1 and 2. Now, the first term of my series, if my sigma is starting at 1, is, plug in that 1, and I get the number 1. That first term is this length. And so what I want to do is compare areas. If I take something that is length 1 and I give it, and I make this a rectangle where this base is a distance of 1, then multiplying the length that is a sub 1 times 1 means the area of this rectangle is the same thing as a sub 1. And it looks like blue is favored over red in this situation. Anyway, A2 is going to be this distance, and then I'm going to take it for 1 unit and say that the area of this is a sub 2. And so as you can see, if I'm dealing with an inequality with just the integral from 1 to infinity and my sigma from 1 to infinity of the same formula, that the integral is less. Now, the other thing that I want to look at is, what if I take the first term of this series out of the mix? So let's say I start at n equals 2. Okay, looks like I'm going to have to redraw a little bit. This time I think I'll use gray, and maybe that will let the red take over. So again, the integral from 1 to infinity is all of this. But in order to really compare sigma and the integral and write an inequality, I have to have the area be looking directly at x equals 1 because my integral is beginning at 1. Now, if I'm starting at n equals 2, then my first term is 1/4. But I'm still going to call that a sub 2. And that a sub 2 is found by plugging 2 into that x. So this length is my a sub 2. However, I need to make the area butt up against x equals 1 if I'm going to be able to compare these two. So the area of that rectangle is a sub 2 by itself. A sub 3 is this distance. So then I take it to the left and see that that is the area of that rectangle is a sub 3. Now I can see very clearly that in this case, the integral from 1 to infinity is actually larger than sigma if I have sigma starting at 2. But if I look at the various inequalities that I have in here, that isn't exactly the way things are. So I need to look at, I've got a whole bunch of stuff where it's 1 plus the integral from 1 to infinity. And I need to look at that inequality with my sigma, because if I look at the integral from 2 to infinity, it has a lot of these integrals from 2 to infinity without the plus 1. The integral from 2 to infinity is going to be less than the integral from 1 to infinity if I'm dealing with positives. So I can say that the integral from 2 to infinity is less than sigma starting at 1 and going to infinity. So let's take a look at what that allows me to have. The integral from 2 to infinity being less than sigma, B and D, both of them do that. If I look at A and C, A and C are both trying to tell me that my sigma is smaller than the integral that goes from 2 to infinity. So those are out. I can at least lessen what I need to cope with. But now the big question is, what about this pair? If I add 1 to the integral from 1 to infinity, do I get that it's greater or that it's less than the sigma that starts at 1? What I can do is I can look at, let me take that out. Let me get some of this just out of the way. I'm going to go back to the sigma that starts at n equals 1. And I'm going to look at the fact that it is equal to, when I plug in 1, I get the number 1. Curious. Plus, then when I plug in n equals 2, I'm getting 1/4, and then I'm getting 1/9, and so on. So what I could actually do is I could look at this equation and what it is equal to. And I can look at the fact that if I subtract 1 from both sides of this equation, then I have sigma from n equals 1 to infinity of my formula, 1 over n squared, minus 1 is actually equal to the sum starting at 2. Those are equal. When I use the sum that is starting at 2, and I look at its inequality with the integral from 1 to infinity, remember that I found that the area under the curve is greater than my sigma that is just starting at n equals 2. Then let's bring in the fact that that sigma from n equals 2 to infinity is identical to sigma from n equals 1 to infinity of 1 over n squared minus 1. So if I add 1 to both sides of this inequality, then I am able to say that sigma from n equals 1 to infinity of 1 over n squared is smaller than the integral from 1 to infinity of 1 over x squared plus 1. And that would be exactly what this statement is saying. So B is the correct answer. A reminder, when you are dealing with an inequality between an integral and a sigma, you need to force to happen whatever the integral is starting at, that x-coordinate. You need to look at what is your sigma starting at. Is it starting at 1 or is it starting at 2? If it's matching that starting number, then you're going to make left endpoint rectangles so that the area can butt up against x equals 1. But if you start with n equals 2 as your very first term, you are 1 unit away from where the area of that integral is beginning. So you have to head to the left and make that rectangle go from 1 to 2 in order to see what the inequality is. I hope that helps.